Hello, good afternoon, everybody. So I will continue on the lecture about the life tables. I pretty much went through all the columns of the life table in the previous class, but I just want to go through the slides as well and going more into detail about what each one of these columns represent. And then I will also show it an example of the life table, the real calculation of the life table using real data in Excel. So as we saw, we have mortality rates, the by age groups or the age-specific death rates, which is also symbolized by the MXN. And with those rates, we have the probabilities of dying, the mortality probabilities. With that, we get the number of people surviving to the beginning of each one of these age groups, the little LX, because this is information about the people surviving to the beginning of the age group. The notation here is not little LXN, but just little LX. And the number of people dying within that age group, so it can be within any of the ages within that age group. So we do have the DXN. And this is the number of person years lived within that age group. And because we have people dying, the number of person years will decrease as we go over into more older age groups. The big TX is the cumulative number of person years going from the bottom to the top. Then we have the total number of person years lived by all these people here that were born in this hypothetical cohort. So 100,000 people were born. They experienced this probabilities of dying. And with that, they would live a total of 7.8 million person years. And if we divide that by the number of people who were born at the beginning of this period, we would have an average of 78.7 years of life experienced by these people here, if they were exposed to throughout their lives to these probabilities of dying, right? So the life table pretty much gives us that. But the life table gives not only the life expectancy at birth, it gives us the life expectancy at each one of these other age groups. Given that someone survived into an older age, how many remaining years of life people should expect to live are these other rows here. And also, we can use this information here as how we would expect our population to be in the future if the overall number of births does not vary a lot in the population and the mortality rates by age group don't vary a lot. See, this is another contribution of the life table. It's not just about only life expectancy at birth. It's not only about life expectancy, remaining life expectancy once people reach specific ages. But we can use this column here as the basis of projections, of population projections for the future, based on the assumption that mortality rates are not varying too much from now to the future, because we reach so low levels of mortality that doesn't change as much, and the overall number of births has been kind of stable. We're going to talk about that. That would be a stationary, a stable population in which we have a constant mortality rates by age groups, a constant overall number of births. We can use this information as the basis of population projections. And then I can make some scenarios. Oh, what about if fertility increases a little bit or declines even further? What about if there is some variation in mortality? And then we can also include the migration component. So the life table gives us a lot of stuff. It gives one overall mortality indicator that summarizes the mortality experience of that population that specific year, summarized here by the life expectancy at birth. It gives us all these other ones here, the life expectancy at birth for someone who reached 40 years of age and they overcame the risk of dying. They did not die at earlier age. Once they reach age 40, they expect to live another additional 40 years, 40.5 years, additional to what they already lived. So they will live on average 80.5 years, more than 78.7 at the top. And more than that, the life table can serve as the basis of population projections. So we'll talk a little bit about this here now. I mentioned this slide also at the end of the last class about each one of the columns. And then I will just go in detail about each one of the columns in the life table. The age groups refer to the range of years between two birthdays, right? So these are completed years. The age group 5 to 9 refers to the 5-year interval between the 5th and the 10th birthdays. So people who are 9 years and 11 months old, they enter in this age group from 5 to 9, okay, as we have done before for other demographic indicators. The probabilities of dying, that first column that we see, is the most basic column of the life table, is the probability of dying for each age group, and it's symbolized by the little q xn. These are probabilities that persons alive at the beginning of an age interval will die during the interval before they reach the start of the next age interval. For the last age group, the QXN equals 1. Everybody dies. Look at this. What is QXN? Is the number of people dying within that specific age group divided by who? By the number of people alive at the beginning of the age group. Going back to the first lecture in the semester, what's the difference between rates and probabilities? Rates, the denominator is person years. If we don't have information about person years, we can get the population in the middle of the period as an approximation, or the average of the population in the beginning and the end of the period. What about probability? Probability, the denominator is the population at the beginning of the period. And that's exactly what little lx is. If you go back to the life table, I mentioned here 100,000 people are people who are born, have 0 years of age. Are all of them going to complete 1 month, 2 months, 12 months? No, some of them will die before that. This information here is about people alive at the beginning of this age group. 99,388 is the number of people alive at age 1, not at age 2, not at age 3, not at age 4, at the beginning of this age group. So since at the beginning of the age group, when I get this information here and divide by this, when I get the number of deaths and divide by this population here at the beginning of the age group, I get probability of dying, not rate of dying. I get mortality probability. I do not get mortality rate. But based on data from the government, mortality data that we usually collect to construct life tables, we get mortality rates because the denominator is the population in the middle of the period. We transform the rates into the probabilities. This one's here. And then from then on, we do the exercise of the life table, okay? That's why we have to do the translation or the transformation from rate to probability. because the LX here is the population reaching the beginning of each one of these age groups. The difference between mortality rates, the MXN, and the mortality probabilities, the QXN, is the denominator. The MXN is the denominator. The denominator is the mid-year population. This is the information, for example, that I got to have the Excel table as the example that I have here for this class, that I got from the CDC, from the Center for Disease Control and Prevention. I got the number of people dying in the US in a specific year for each age group, and the population in each one of those age groups is the population in the middle of that year. It's not the population at the beginning of the year. The denominator is the population alive at the beginning of the age interval, right? So we do this transformation here, and then we start the process, as I said before. The little LX is the number of people alive at the beginning of the age interval, known as the little L column. So these terms are terms used by demographers: little L column, big L column. It is calculated by subtracting the number of people dying from the little LX value in the age interval immediately preceding the one being calculated. So in practice, what do? That's what we showed in the previous class. We get the mortality rates, use a formula to transform it into probabilities here in this table. Start with an initial population, multiply this by this, we get the people dying. This one minus this one, people surviving to the next age group. This one multiplied by this, people dying. This one minus this, population alive in the following age group. This one times this, number of people dying. So step by step, that's how you do these calculations. So from that one, of the 99,224 people alive at the beginning of the age interval from 10 to 14, 99,224. This one times this probability of dying, 70 people will die. If 70 people die between the ages of 10 to 14, this minus this, we will have this amount surviving to age 15, right? So we will have exactly 99,154 people reaching age 15, because 7 of them died between the ages of 10 to 14, symbolized by the D10-5. And the 5 includes 10, so that's the age group of 10 to 14. Number of deaths is number of people dying within that age group. That's why we have the interval DXN. And DXN equals number of people who survive to the beginning of the age group multiplied by the probability rate of people within that age group. So the number of people dying between the ages of 40 to 44 equals the mortality probability of those between 40 to 44, and that table was 0.009979. Number of people alive at the beginning of the age group, 96,798. And then the number of people dying in that age group from 40 to 44, 966 people. So that's pretty much this exercise here. All right, so just multiplying this number by this number, we get this number here. The years lived in the age interval, the big L column, is the total number of years lived by all persons who enter that age interval while they are in the age interval. In that, let's say a life table with 5-year age groups, and we have the radix, the little L0 equals to 100,000. If nobody dies, everybody keeps living. If I leave one person in the age group from 5 to 9, 5 years, and I don't die, I will contribute 5 years of life in that age group because I will reach age 10. So I will contribute 5 person years. One person contributes 5 person years. Some people will die at age 8. So that person will contribute only 4 years, 5, 6, 7, 8. Some people will die at age 5, so that person will contribute just 1 year in that age group from 5 to 9 in the big LXN column. So here, 5 to 9. If someone here survives only until age 5, that person will count 1 unit here. Age 6, that person will count 2 here, and so on. If that person lives until age 10, that person will count here from 5 to 9 5 times, 5 years, 5 person years, right? So out of the 98,011 people who are alive at the beginning of the age interval, 30 to 34, so 98,011 people survive up to age 30. If none of them die during that age interval, they would have lived a total of 490,055 years. Would be this 9811 times 5. 490, 55. Go back to the table. These people here, if nobody had died and everybody reached age 35, this number times 5 would be 490, 55. But some of them died, 539 of them died. So this number is going to be lower than 490, 55, right? How that discount is made, we use a formula with some assumptions that some people will likely die at the beginning of the age group, some people will die in the middle, some people will die at the end of that age group. So the formula for the big LXN is more complicated because we have to take into account that some people die more at the beginning and some at the end. For younger age groups, people who died between the age 0 to 1 usually die closer to 0. Afterwards, we say, oh no, people die in same ways between, for example, 30 to 34. But here, people die closer to 0, and here people die closer to 1. So we have specific formulas for the big LXN column for the first age groups. And also for the last one, right? Because we don't know exactly if people are dying at age 100, 101, 102, and so on. So we have to make an adjustment there. Now I'm going to show you in the Excel table. So we have different formulas for the big LXN because of this issue that I just said. So demographers assume that deaths are roughly distributed during the 5-year period for most of the age intervals. The ones in the middle of the life table, we say, oh, people die with the same chances between 10 and 14, between 35 and 39, between 30 and 34, and so on. But this assumption does not apply to the first few age groups. So there are several formulas to produce the LXN value for the first few age groups, because the first age groups, such as 0 to 1, 1 to 4, when children die, they die closer to the first ages of those age groups. Those children that die between 0 to 1 are usually related to more genetic diseases, and they are much higher closer to age 0 than to age 1. The same thing between 1 and 4. Children, whenever they die in that interval, they die closer to age 1 than to age 4. And like I said, at the other extreme, for the last row in that life, 100 plus, another formula is used as well to estimate what's the average number of years that people that reach at least 100 years of age will live from then on. And then the years lived in current and subsequent and in the following age intervals is given by the TX. That's the total number of years lived by the population in the age interval where we are, and in all subsequent age intervals after that. So it's pretty much the cumulative results of the big LXN column, summing, adding up from the bottom to that age group that we are calculating. So that's the formulation. It's pretty much getting the TX for a specific age group. You just get the big LXN in that age group and all the ones following it. So the sum will be the sum of the LXN columns starting at entry X, and going until the last entry symbolized here by W. And one example for the T95, just a simple example here. The last one, the T95, go back to the table. This one, how do I calculate that? It's pretty much 24,670 plus 4,542. That's the value that we have here. Okay? 229,212. And then the life expectancy, or the most appropriate name, remaining life expectancy, or average number of years of life remaining at the beginning of that specific age group. For each one of the rows, you get the value of the TX and divide by the little LX. So for example, for that life table, the life expectancy at birth is the T0 divided by the little L0, 78.7. And the E25 is 54.7. What does it mean? This E25 means that people who lived up to the age of 25, they could have died between 0 and 24. They did not die. They were exposed to the chance of dying, but they did not. They survived. Once they survived, how many years after 25 are they expected to live on average? The remaining life expectancy at the beginning of that age interval, at the beginning. This is the age group from 25 to 29. When they reach at that beginning, how many years on average? More? 54.7. So 54.7 additional years on average. 54 plus 25, 79.7. 79.7 here is higher than 78.7. 78.7 is just saying, if people were exposed to those chances of dying throughout their lives, they will live on average 78.7 years. But when some people keep going on, they will gain some additional years of life on average. One column that's not in the life table, but it's a good column to have, it's called the average age at death. It's pretty much the remaining life expectancy, EX, added to the age X, the age at beginning of that specific age group. So the EX is the expectation of future life beyond age 0. It is not an average age at death. Oh, but what about the life expectancy at birth? The life expectancy at birth, you said that's the average age at death for people who experience those mortality probabilities. Why is that? Because in that case, we get the E0, 78.7 in that exercise, and add to the age in the beginning of that age group, which is 0 to 1. So here's 0. 0 plus 78.7, you're going to have 78.7. But for the other age groups, you have to add the x's. We add x and EX to obtain the average age at death for cohort members who survive to that age X. Not all life tables include this column. And always the X plus EX column goes up, because once I reach a further age group, I didn't die because of previous chances, so I gained some additional years of life. But the EX column does not always go down. It often goes up after the first years of life, because some babies who survive infancy, who survive the first age group from 0 to 1, are no longer at risk of dying to those high infant mortality rates. So sometimes the EX column can go up a little bit from the first to the second age group, okay? So in this specific example here, since mortality, infant mortality probabilities is really low in the US, the EX here goes down from here to here. But if I have a country with much higher infant mortality probabilities, the life expectancy, the remaining life expectancy could go up here and then start to go down, right? But the X plus EX column, if we add it, it's going to be always a number going up, because people will gain bonus of life if they survive chances of dying and they don't die. Cool? If we get those columns from the life table, the mortality probabilities, the QXN, if we get the number of people dying, the age intervals, DXN, if we get the number of people surviving to the beginning of the age group, LX, if we get the number of people, the remaining life expectancy for each one of the age groups, EX, those would be the usual curves that you get from each one of these columns. If you just get those columns, then you make a line graph. So for probability of dying, infant mortality rate is usually high, and then it declines for the next age groups, and then it starts to increase again until it gets really high at older age groups. The number of people dying is high because this at the beginning of the life table, because usually when we have high infant mortality rates, infant mortality probabilities, and then it goes down, and then afterwards starts to increase the number of people dying. But then, although the probability of dying is high, there are not so many people left in our life table after a specific age. So the overall number of people dying starts to decline. The little LX column, we talked about it, the red X, the beginning of this column, is that hypothetical cohort that we experienced as the probabilities of dying. It can be 1, 1,000, or 100,000, for example. And this number, as we apply the chances of dying to these people, the little LX column starts to decline until we get into the last age group and everybody dies. And the remaining life expectancy for each one of the age groups usually declines, but for countries that have high probabilities of dying, in the first age groups. Once I reach age 1, I will have overcome this high risk of dying before, so I will get some additional bonus of life, even further. And then it starts to decline again. Okay, but if I want to know the average age in which people die for each one of the subsequent age groups here, I have to add the remaining life expectancy to the age at the beginning of each one of these age groups, as I showed before. So Alfred Lotka, he used these life tables in the development of his stable population theory. And this is what I was talking to you, the use of life tables for population projections. So the life tables here are not taking into account migration, right? It's just mortality and fertility. Where is fertility? Fertility is the little L0, is the radix, the number of people born that will be exposed to the age-specific probabilities of dying. So the exercise of the life table is an exercise of a closed population. What does it mean, a closed population in demography? Is that we are taking into account mortality and fertility trends, but we are not taking into account migration. We are not taking into account people moving in and moving out. If a population that is close to migration experiences a constant schedule of age-specific fertility and mortality rates, it will develop a constant age distribution. It will grow at a constant rate irrespective of its initial age distribution. So just go back to the life table. Just go back to the life table. The life table here has mortality here and fertility. Let's say that these probabilities of dying by age groups don't vary a lot. Whenever we have a pandemic and then the mortality rates, the mortality probabilities vary a lot, of course, this stable population theory becomes weaker. But let's say that in these last few decades, the mortality has been low and stable over time in the US. So these rates here, or these probabilities here, have been overall constant. If these probabilities are constant, and the number of people being born in a specific country has not been varying so much, we can use the information from this big LXN column here to predict how it's going to be the age distribution of that population. If I add all these numbers here, how much is it? If I add the column LXN, everything in column big LXN, if I get all these numbers here, add them up, I get 7.8 million. So if I get this number here, 99,465, and divide by 7,866,000, I get the proportion of people in that specific age group. This number here divided by this number here divided by this, I'm getting the proportion of people in each one of these age groups. If I prefer percentage, I just do the same division multiplied by 100. So just by getting the big LXN and divided by the T0, I can generate the age distribution of my population. Is that the real age distribution of my population? No. That would be the age distribution of my population if the mortality probabilities don't vary too much from now and in the next few decades, and the overall number of births don't vary too much from now to the next few decades. So this column here will be how I expect my population to be distributed by age group. But this column makes sense to analyze in proportional or percentage terms. That's why we divided each one of these numbers here by the T0. Okay? So here are the final, these are the slides that I had for life table. These ones here are all additional slides. I will not go into a lot of detail about them. But overall, I mean, there are different ways to analyze a life table. And what I want to just show you, and here we go in more detail, how are the big LXN columns being estimated. This values here, I would expect you to understand it or to know it, that for the first age groups, you will have more people dying at the younger ages. So for the 0 to 1 age group, when you calculate the big LXN, you multiply the number of people dying by 0.85, and then you subtract the LX by that multiplication and multiply by the width of that interval, which in this case is just 1, 0 to 1. But 0.85 means that most people in the age group from 0 to 1 are dying closer to 0, because the number symbolized by the letter A here is greater than 0.5. For 1 to 4, A is also greater than 0.5, meaning that when children die in that age group, they die closer to age 1 than to age 4. For the odd age groups, A, we assume it to be 0.5, that people have the same chances of dying, for example, from age 10 to 14, from age 35 to 39, right? The formula of the big LXN varies from different textbooks in demography. I will show you an Excel table using specific formulas from one specific textbook, but you could see variations of how these formulas are estimated. And for the oldest age group, you can use the little l 100, number of people who survive up to age 100, and divide by the mortality rate at age 100 to get the number of years lived in the last age group, okay? This is the same thing. And what I was telling to you guys before, usually the way that we interpret the life table is with the synthetic cohort interpretation. How is it? If I expose a group of people to these mortality rates throughout their lives, they will live on average this amount of years, symbolized by E0, life expectancy at birth. But let's say that the mortality rates by age group are not varying too much, and the overall number of people being born are not varying too much from now into the future. So we can use that stable population theory. And more specific, we can use a stationary population assumption, that our population will not increase or decrease in size anymore. How do you know that our population is not increasing or decreasing in size anymore? That the number of people being born and the number of people dying are equal for each year. Hey, where do we have that in the life table? Where? For example, this is other life table here. Just going back to the stable population theory. The stable population theory said, If I have constant age-specific fertility rates and mortality rates, my population will have a stable age composition. Doesn't change so much the number of people in each one of the age groups, but the population can grow or can decrease at a constant rate. So it can grow, positive rate, or can decrease, negative rate, but at a constant rate. But when I get the big LXN column, I'm getting the result from this specific life table here. So this is another life table, but using that same format. Here, starting from the beginning, the population, number of people dying, population divided by number of people dying, we get the mortality rate, and then we transform the mortality rate into mortality probability. And then 100,000 people are born, and then we start to apply the chances of dying and getting the deaths here. What is a stationary population? What is a stable population? A stable population is when I have a specific group of people that are growing in terms of population rate at a constant rate over time, or decreasing at a constant rate. Every year, let's say the constant rate of the population is of 1% or minus 1%. When it's constant over time, is a stable population. There is one example of stable population that can also be called stationary population. The stationary population is the example of a stable population in which the age composition is not only constant, but also the population size is constant. The population rate of growth equals to 0. Is not +1, +2, is not -1, -2%. Is 0. Where do I get here from the life table that I have the same number of people being born and then the same number of people dying in that specific year? Where do I get information about how many people are being born in the life table, of any life table? Where is the number of people being born in this life table here? How many people? Is the radix, the little L0, 100,000. 100,000 people are being born to do this exercise. How many people are dying? Where do I get this information from? How many people are dying? If I'm saying that's a stationary population, then the same number of people who are born are dying. If 100,000 people are being born, how many are dying? 100,000 people. Where do I get that information from? I just add all these rows here. When I add all these rows, including the groups in between, I get how much? 100,000 people. These people here, 100,000 are born, and then everybody dies in this exercise until the last one. See? 2,411, 204,011 died. Everybody, 100,000. The same number of people are born and dying. We have a stationary population. When we have this possible exercise, we can interpret our life table as being the result of this unchanging age-specific mortality rates and a constant number of births and deaths. What is the constant number of births? The radix, the little L0. That's the same number, which you can also get by summing up the column of DXN. When you do that, you can get the big L column here and estimate the distribution of the population in the case of unchanging age-specific mortality rates and number of deaths equal the number of births. the real population distribution for the US 2007 using this data, you get it from here, from this column. And here we have women, and here we have men. Getting these columns here and showing them in percentage terms, we have this age-sex structure. Going back to the life table and getting this column here, we get the population distribution, the stationary population, which is this one. This data is from the big LXN expressed in percentage terms. So what does it mean? That if the age-specific mortality rates don't change much from now into the next years, and the number of people dying and being born is the same, this is what we will expect the age-sex distribution to be in the US in the future years. So pretty much when we have a stable population, it doesn't matter how it was the population distribution in the past. The future kind of forgets the past and gets into this more rectangular shape of an age-sex distribution, right? I think that's what something that I mentioned here, that the population, the age distribution of the future forgets how it was before. Cool? These are more advanced topics. Let me show you the Excel files. If you go in the course website under mortality, there is this file, this link here to example of standardization in Excel, example of life table. These are compressed files. If you uncompress them, under the life table, one of the files is this life table here based on the textbook by Wachter. And what do we need to generate a life table and do all those calculations? We need the population by age group. We have here the age groups and the number of people in each one of those age groups, right? 0 to 1 until 100 plus population here, and the number of deaths in each one of these age groups. And we have it for women and for men. Where did I get this data from? I got it from the Center for Disease Control and Prevention, the CDC, in this website here, right? And this is data from 2017. The population data just goes up to 80 plus. So what I do here for this exercise, I will add up the 80 until the 100 plus people dying here into 80 plus. Okay, and do the same for men. So the last age group that we have in my life tables would be the 80 plus because of this limitation here of the data that's available in that website. So we organize the data. This is the raw data. I will organize the data. This is it. 0 to 1, 1 to 4, and then the 5-year age groups, 5 to 9, 10 to 14, and so on. So pretty much getting the data from before. And then the last one, 80 plus, I add up those last rows, 80 to 84, 85 to 89, and so on. And I also have the width of the age group. The first one is 0 to 1, so 1 year, 1 to 4, 4. The other ones are 5, and then the last one is an open age group, open-ended age group. We have numbers of deaths, of women by age group, of men by age group, and the population. This population, when we get from these data sources, is the population usually considered at the mid of the period. So if we divide the deaths here, this column, by this one, we get the rate, because the probability is the population the mid of the period. So let's use this data here to estimate a life table for women, this data here to estimate the life table for men. Life table for women. And just remembering, these are all the formulas that I will use here in this exercise. And I do ask this information about A's in quizzes and exams. So this is good for you to know. And it's all open book, so just be prepared from now on before you take quizzes and exams that will contain mortality. Be prepared. That's where usually people get the lowest grades in this course. The first age group goes from 0 to 1. Goes from 0, has a width of 1. This one has a width of 4. 5, width of 5. So goes to 5 to 9, and so on, until the last one that's an open-ended interval. The AXN is that column that we say, what is the average years in the interval for people who die in the first age group from 0 to 1, in the first one here, they will die much closer to 0. So the average years in the interval is only 0.1. For people who die between 1 and 4, those that die will die closer to 1. So AXN is 1.5. 1.5 is closer to 1 than closer to 4. Right? And for the other ones, the average number of years, the best way to describe it, the best way to explain the AXN. If people who died between the ages of 0 and 1 were dying with the same chances between 0 and 1, how much would be AXN? Just divide n by 2. Would be 0.5. But it's 0.1. Instead of 0.5, it's 0.1. So it means that those who are dying closer to 0. If those who die between 1 and 4 were dying the same chances between 1 and 4, how many years on average would they live in the interval? 2. 4 divided by 2. But how many years on average they are living? 1.5. What does it mean? That those that die between the ages of 1 to 4, when they die closer to 1 than to 4. If it was equal, the AXN would be 2, not 1.5. If this one here, the chance of dying in the interval was equal, AXN would be 0.5, not 0.1. What happens in the following ones? People dying between the ages of 5 and 9. If they die with the same chances between 5 and 9, how much would it be? 5 divided by 2, 2.5, exactly what we have here. That's the assumption that we have for all these age groups. Cool? How exactly were these data here estimated? Using this book, Essential Demographic Methods from Wachter, this book here. What are the formulas that he proposes? For the first one, you get the infant mortality rate, M01, multiplied by this constant, 1.7 plus 0.07. How do I do that? Remember, what is the population of women in the US in 2017? Where did I get this data from? They all come from the organized data sheet that's right here. 1.9 million is here. And the number of deaths, 9,867, is here. If I divide deaths by the population in the middle of the period, I get the age-specific death rates or age-specific mortality rates. This one's is just dividing deaths by population. This one here is the number of people dying before reaching age 1 divided by the number of people who were born in that specific year. This rate here for this first age group is the infant mortality rate. Is exactly the M01 shown here at the bottom of the table. So for the AXN, how do I calculate it? Just implement this formula. This cell here equals 0.07 plus 1.7 times the infant mortality rate. So the 0.1, the 0.1 will vary from one life table to the other because it is based on observed data, the infant mortality rate. The 1.5 is an assumption that we have that based on historical empirical data from 1 to 4, instead of having an average chance of dying equals to 2 years, on average it's going to be 1.5, closer to 1. And this is pretty much a constant. For the other age groups, it's pretty much the width divided by 2. What about the last one? For the last one, the average number of years that people will live once they reach 80, in this case, it will be 8.4. How do you calculate that? You get 1 divided by the last mortality rate. 1 divided by 0.2084 in this case. And that will force everybody to die in that specific, in that end of that age group, right? These formulas here vary by specific textbooks. Whenever I'm asking in the quizzes and exam, it's going to be based on this Excel table here. Okay, now we understood how we calculated the A's. The M's I told you is just the number of people dying divided by the population. What is this T? Is the time period that I'm talking. Since the T here is 2017, 1 year only, I don't have to multiply by anything because it's just multiply by 1. And then it comes a more complicated formula. Translating the mortality rate into the mortality probability, transforming MXN to QXN. I pretty much get here the width of the interval, in this case is C4, multiplied by the mortality rate in that age group, which in this case is exactly G4, is right here, because here we are on H4, divided by 1, plus the width of the interval, the same C4, minus the average number of years in the interval, multiplied by the mortality rate again. So based on this data, this, and this, I get the QXN. I needed the mortality rate, the width, and the average number of years in the interval. I get the probability of dying. Do I expect you to know this formula here for the probability of dying? No. This is just to show, there are different ways to calculate it. And it's just an overall, it's a way to transform the rate, which has the population, the mid of the period in the denominator, into probability, in which the denominator is the population in the beginning of the period, and more specifically, in the beginning of the age group. For this one, The denominator are people at the beginning that reach age 0, that reach age 1, that reach age 5 to calculate this one here. Okay? And then at the end, for all of them, we just follow that same formula. And then at the end, everybody dies. 100%, everybody dies. In the previous one was 13% of the people died, 0.1384. And here is 100% of the people are dying. And now we start the exercise. The radix, using that same radix that we had before, of 100,000. This hypothetical cohort of people, 100,000 people, that will experience these probabilities of dying. If these people here that are born experience these probabilities of dying between the ages of 0 and 1, how many will die? 510. Just multiply this by this, right? So the D is pretty much equals to the probability of dying multiplied by the number of people who survived to the beginning of that age group. How do I calculate the next LX? The people who reached the previous age group minus the number of people who died throughout the last age group, which will be this number minus this number here. Can do 100,000 minus this number here is 99,490. And you can accomplish that same result by doing this other exercise here. 1 minus the probability of dying is the probability of surviving. 1 minus the probability of dying is the probability of surviving. Probability of surviving multiplied by this is the number of people surviving to the next age group, which is this formula here. You can implement either this formula or this formula here for these guys. And the D, what I did, just multiply this by this, this one here. But I also could use this formula. This formula gives the same result as this one, and this one gives the same result as this one. Until the last one, in which if we get 75,000 people here, 10,000 died during that interval, 65,000 survived to the next group. How many will die? 100% of those people will die. 1 times this, everybody dies. And then we come to the big LXN column, the number of years lived in that interval. Here the formula is simplified. For the first age group here, for 0 to 1, these people here were alive at age 0. These people here were alive at age 1. They all survived to the next age group, 99,490. How many years these people, how many person years these people here lived in the previous one? The previous age group was from 0 to 1 year. And they all survived. So it's 1 times this, right? 1 times this. Where do I get that? I just multiply this number here, which is I5 times C4, where C4 is exactly the width, 1. What about these people who died? These people who died, 510, they were born, but they died before reaching age 1. How many person years do they contribute to that big LXN cell here, the first one? We have to get the approximation of what's the average number of years that these people who died survived. For those who died, how many years on average they lived? Where do we get that? From here. That's the formula. We get the number of people who died, 510, and multiply by the average number of years that they lived before they died, 0.1. So 99,000, for those that survive, 99,000, we multiply by N. For those who died, we multiply by A. And that's the formula here. And that's exactly what we are doing. I5 multiplied by C4 and D4 multiplied by J4. We do the same thing for the next ones. For this one. These people here were alive at age 15. This 99,146 reached age 20. So how many years did these guys here live in the previous one? 99,146 times 5. C8 times I9. What about the 146 who died? The 146 who died, they lived on average 2.5 years. The D8 multiplied by J8, and then you add these two numbers, right? And for the last big LXN, you can simply get the number of people who died multiplied by the average number of years that they lived in the interval, which we calculated here before, 4.8, right? D, the big LX, D, I didn't put it here, but it's, oh yeah, right here. D multiplied by A. D multiplied by A, but there are all these other ways to show the same formula. And the TX, we add from the bottom. This one is just this cell. This one is these two cells. This one adds these three. This one adds all these cells until this one that adds everybody. And then the EX column, we get the number of person years in total that all these people live from 0 until the end, divided by the number of people who were born. Here, the number of person years that people live from here until the end, divided by the number of people who were alive at the beginning of this age group. And then we do to everybody. And then the column that we didn't have before, you can get this column here and add to the age at the beginning of this age group. That's the reason that I have this column here. The age at the beginning of each one of the age groups is 0 for this, 1, 5, 10, 15, until 80. So the average age of death, this last column here, for example, for these people, once they reach age 1, they will have some additional years of life. Instead of living only 77.9, on average, it will be 78.3. These ones here who lived up to the age of 65. Up to the age of 65, they will live an additional 17 years of life after they reach 65. 65 plus 17, they are expected to live on average 82 years of life. 82 years is higher than 77.9 because these people did not die to previous causes. So they overcame those obstacles and survived more throughout their lives. So this one here is for women. This one is the same exercise for men. One other thing that we have here at the bottom, or this column here is just to check if we did the calculation correctly. Just dividing the number of deaths by the big LXN, and this number here, it's the same as these numbers here. And the crude death rate, what is the crude death rate that we calculated before? The crude death rate is that simple rate of mortality. How do you calculate that? We get the overall number of people who died in a specific population divided by the overall size of that population. How many people died in this life table here? As we talked before, 100,000. These 100,000 people here, how many died? If you just add these people here, this column, how many died? 100,000. So the crude death rate will be the L0, the radix, 100,000, divided by this overall number of person years. Remember, the denominator of demographic rates, the ideal will be the total number of person years lived by these people. And the total number of person years is the T0, which adds up everything here. So this one is pretty much this number divided by this number. If I want to multiply by 1,000, how do we interpret that? Based on data for women, for men, here's for men in the US in 2017, for every 1,000 people, around 13 people died, men died in the US in 2017. Right? So see how much information we can get from a life table. The age-sex structure, we don't need the life table, right? We just need this column E here for men and for women. We can get this column E here for men and for women and estimate the age-sex structure. So for men here we added these two, 0 to 4, 2 million plus 8 million, we get 10 million. And then the afterwards is the same, 10.3 is the same number here. Get this information in absolute terms, put it to proportion or percentage. We have the age-sex structure. But for this, we don't need a life table. But for the life table, if we do the same exercise using column K in this spreadsheet, what is this big LXN? Is the number of person years lived if people were exposed to those mortality rates. In a stationary population, in which mortality doesn't vary from now and the next decades, and the number of people being born does not vary from now in the last decades, and the number of people being born, 100,000, equals the number of people dying, 100,000, this would be the population, male population in the US. But of course, we would express it in percentage terms. So we pretty much get these results here from big LXN column and put them here. Just remember here for this age-sex structure, I get the 0 to 4. So I add up these two cells, 0 to 1 and 1 to 4. These two here, I add up here. And then afterwards, then 496 is the same thing here, 496 to 27. Based on this ones, I estimate the percentage distribution. And in this case, I divided each one of the age groups here of women by the total of women. I could also divide it by the total population if I wanted. And then we get the age-sex structure of the US in the future if the age-specific mortality rates in the US did not change much from 2017 forward, and the number of births were equal to the number of deaths. Is that feasible? No, mortality rates change now, increase now because of opioid crisis, because of the pandemic. Fertility also varies a little bit. And in the US, we have still a lot of immigration more than immigration. But we could start from this projection and then create some scenarios for mortality, for fertility, and for migration, right? So that's a really powerful exercise. And the standardization, the other spreadsheet that's available in our course website, here I'm not going to go in detail, because we already showed you in these slides exactly the original crude death rate for the US, for Venezuela, and then I showed you the exactly exercise that we do, getting the observed rates for Venezuela using the population of the US as the standard, the proportional population, and then you get the standardized rate, the crude death rate for Venezuela using the US as the standard. Then you see that the Venezuela crude death rate is not smaller than the US, it's actually higher when you control for age structure. And all those graphs that I showed in the slides, I created them in this spreadsheet here. Like I told you guys, here, for example, is the age-specific mortality rates for all age groups. If I do a zoom in the first age groups, I see that the age-specific death rates for Venezuela are always higher than in the US. Here, it looks like they're all the same, but if you take out the old age groups, they're always higher in the first age groups, okay? But all these graphs are the ones that I showed in the lecture, and I provide the Excel table so you guys can make the same exercise with other data that you might get. So the quiz is now open, and the quiz is going to be about standardization and life tables. So take your time, prepare your material before you take the quiz, and have a great weekend. And I see you guys on Tuesday. Thank you.